Hello everyone. In this session we are gonna go through multiple pipe systems. So if you remember from last session we went through single pipe systems. We introduced three different problems that type of problems that we can solve in single pipe systems, type 1, type 2 and type 3 if you remember. And now in this session I'm going to go forward and talk about multiple pipe systems. So what if you have many pipe systems that work together and you want to find the discharge or the best pipe design for this type of systems. So this is the objective of this session here. So we are going to introduce different type of multiple pipe systems, including series, parallel, or other things, and then we are going to also we are going to start with introducing the analogy between the multiple pipe systems with in fluids with electrical circuits, and then we are going to introduce series pipe systems, and we are going to solve one example for that, and then we are going to go through other type of multiple pipe systems and solve another example on what is called three reservoir problems. Okay, so let's get started. So the governing equations or the governing mechanisms for the flow in multiple pipe systems are the same as for the single pipe systems. So the fluid equations are the same, right? It's just we are investigating a different application, which is for multiple pipe systems. So now we are going to introduce what are the different, like how you can tackle these kind of problems and how you can find the solutions for a multiple pipe system. Essentially we are going to use the same governing equations, that is mass conservation equation and energy equation, but with a particular focus on this application, which is for multiple pipe systems. But before delving into the details of multiple pipe systems, I would like to bring an interesting analogy with electrical circuits, because essentially there are many of the terminology that we are going to use are similar to electrical circuits, and also there is a kind of underlying kind of similarity between these two systems, because they are both created of like discharge or like these currents that we observe. So I don't know if you remember, but one of the governing equations in electrical circuits is Ohm's law. So Ohm's law relates the voltage in an electrical system with current and resistance in that system. So as you can see, this is the equation for that, which is E equals to I times R, where E is voltage, I is current, and R is resistance. Okay. So we have a similar equation in fluids and fluid mechanics, and that is where we kind of relate pressure gradient with flow rate and a kind of a measure of a resistance in the system, which is kind of friction. Okay, so this is the kind of equivalent equation of this Ohm's law in fluid mechanics system, which describes delta P, which is pressure gradient, equals to Q square flow rate, square of flow rate, times R, which is kind of a measure of resistance, and it's proportional, alpha here means proportional to friction. So for instance, for a simple flow, we found that delta P equals to rho V square over 2 times FL over D. where this is kind of the friction in the system, and this is like kind of similar to flow rate. So you can see a clear analogy between this Ohm's law and the governing equation in a fluid system. So as you can see, the voltage kind of is analogous to pressure gradient in our fluid system. The current in an electrical circuit is analogous to the flow rate in our fluid mechanics system, and the resistance in an electrical circuit is kind of analogous to the friction or losses, major or minor losses in the system, in a pipe system. So as you can see, we have a very similar system to an electrical circuit, which we can kind of find some analogies between them. And now, based on this, we are using the same kind of terminology. But before going through that, I want to just note one main difference between these two systems. So the main difference between the electrical circuits and fluid mechanics or like pipe systems is that Ohm's law is a linear equation. So as you can see here, we have a linear simple equation equals to IR, whereas fluid equations are mostly nonlinear. So generally they are nonlinear, and so here you can see that we have like V square and Q square. So, and also more nonlinearities that we have not discussed in this course, but are caused from like governing equation fluids, like the governing momentum equation, which is a completely nonlinear equation, which I briefly mentioned. If you remember, it's called Navier-Stokes Equation. So let me just write it down here. Navier-Stokes Equation. So if you remember, that is kind of one of the governing momentum equation differential form for fluids, which is essentially a nonlinear equation because of the convection term inside that. So these fluid equations are generally nonlinear, especially for high Reynolds number flows. So for high Reynolds number flows, there is a difference between main difference between Ohm's law and fluid equations. So other than this main difference, there are many similarities between pipe systems. So for example, and also electrical circuits. For example, similar to electrical circuits where we have series or parallel electrical circuits, if you remember. So these were where we put these resistances in series, and then sometimes we could put the resistance in parallel, and this was like the voltage difference in the system, and then we could calculate the I or the current in each direction that the voltage was going. So similar to this electrical circuit analogy, for pipes we can also have series or parallel pipe systems. So in this session I'm going to introduce this same analogy for pipe systems, for series or parallel pipe systems. And then we are going to solve one example for series, and then another example for a multiple pipe system. Okay, so first let's start with series pipes and see what are the governing equations for those and how we can tackle this type of problems. So here is an example of a series pipe. So series pipes are pipes that are connected to each other in series, so one after another. So here you can see, for example, we have three pipes that are connected together. So pipe 1 with diameter D1, pipe 2 with diameter D2, and pipe 3 with diameter D3. So each of these have different areas or cross sections, and the velocity in each pipe is going to be different. So this is going to be V1 here, V2 in pipe 2, and V3 in pipe 3. Okay, so now let's look at what are the governing equations for this pipe system. So the governing equations are similar to before. First one is conservation of mass. So conservation of mass says that the mass, the flow rate that is coming into this pipe should equal to the flow rate that is exits this pipe flow system. So the entrance should equal to the exit. So this means Q1 should equal to Q3, and also it should equal to the flow rate, volume or mass flow rate here. So we can say Q1 equals to Q2 equals to Q3. So this is the first governing equation that we can use for series pipes. And then the second kind of equation that we can use is for the head loss between point A and point B. So the total head loss between point A and point B is gonna be the sum of the head loss in pipe 1, which is HL1, plus the head loss in the pipe 2, which is HL2, plus the head loss in pipe 3, which is HL3. So the total head loss between point A and B is gonna be the sum of these three head losses. So these are two equations that we can use in a series pipe, and with these equations we can solve the different problems that are given to us in this context. So let's see what is the HL. So the head loss is the sum of the major head losses in the system plus the sum of the minor head losses in the system. So the major head losses were caused by friction in the system, and the minor head losses were caused by like additional components in a pipe flow system, which can be like joints, or it could be like elbows or faucet or gloves, or all these additional components in a pipe flow systems will lead to a minor head loss in the system. So this is gonna be the head loss. And for the major head loss, as we said, it's because of the friction in the pipe. So we can show it as F times Li over Di for each pipe, multiplied by Vi square, which is the velocity at each pipe, over 2G, plus all the minor losses in the system, which have their own KL, which is loss coefficient, multiplied by Vj square, again the velocity at each type, over 2G. Okay, so this is gonna be the loss in the system, and we can combine these two together because we know that Q, the mass flow rate, is gonna be the same in all these pipes, and so instead of Vi, I can write, so as you remember, V equals to Q over A, right? So Q over A. So I can just substitute Q over A instead of V. And then because Q's are the same for all different pipes, I can factor that out and come up with this Q square over 2G, which is out here. And then we are only left with F over A square times L over D plus the sum of KL over A square. So instead of V, I just wrote down Q over A, and this will be the total head loss in a series pipe system. Okay, so this is one equation that you can use for finding the head loss in a series pipe system. So now we can have again different those three type of problems that we had for single pipe systems, but for a series pipe system. So if you remember, for type 1, if Q was given, it was straightforward to calculate HL or delta P, right? So this is the type 1 problem where we have the Q, and now that you have Q, you just write the energy equation, and then you calculate HL or delta P. So this is pretty easy, and we can do that. For type 2 problems, where the problems were delta P and Q were given, delta P was given, and then we wanted to know what is Q, right? We wanted to know what is the flow rate in the system. So in this type of problems, we need an iteration scheme, which is a trial and error to find the friction factor, okay? So in this type of problems, they are a little bit more difficult because we need to do some iterations, and because they are kind of nonlinear, we don't know Q a priori, and we don't know the velocity and head loss. And in order to find the velocity and friction velocity, we need to have the energy equation. And for the energy equation, we need to know the friction factor to find the head loss. And for friction factor, we need Reynolds number, and Reynolds number in which is dependent on velocity. So if you want to use Moody diagram, we need to know velocity, and but that is kind of an unknown in our problem. So we need to use an iteration scheme. So we need to assume a velocity or friction factor, and then go through it again and again to make sure that all the equations are satisfied at the same time. So if you remember, we saw the example of this in the last session. So type 3 problems were the problems in which we didn't know D, or diameter of the pipe, so we need to find what is the pipe diameter. And in this type of problems, again, we need an iteration scheme. And after you do iteration over D values, then you can find optimum D value in which it satisfies all the governing equations, which are the mass conservation and energy conservation equations. Okay, so now that we learned how to calculate flow rate and head loss in a series pipe system, now let's solve an example for these type of problems. And so in this problem, we want to see how to use those governing equations we mentioned for series pipes, and to find the flow rate in a series pipe system. So As you can see, this is here we want to calculate the flow rate into the ditch, and so this should be problem type 2, right? Because we want to find the flow rate in this system, and the delta P, or pressure gradient, and also head losses are kind of given indirectly here, and we need to find them, and we have to calculate the Q, or flow rate, into the ditch here. Okay, and this system, as you can see, is consists of a series pipe. So here we have a pipe, and then we have an elbow which is connected to the second pipe, and then we have the third pipe after the valve, the gate valve. Okay, so I just want to note that in a more difficult problem, these three pipes can have different, this one, and this one can have different pipe diameter, as I showed, as we saw here, right? We saw here it can have different pipe diameters, but this example is a simple one where we have the same pipe diameter, which is 4 inch. And also the problem gives us the type of the pipe, which is a steel pipe, and we have the elevation from point A to point B. We have the length of the pipes. We have the loss coefficient for this gate valve, which is half open, and we only don't have the loss coefficient for this long radius elbow, which is threaded elbow, and we should find it from tables in order to find the total head loss in the system. And other than that, also we have to find the major head loss, and then using all this information we should be able to find the Q rate, the flow rate, and calculate Q. Okay, so now let's get started, and we start by writing the energy equation between point A and B. Okay, so the first assumptions, or first things that we can learn from this problem is P at A, pressure at A, equals to the atmospheric pressure, because it is in the vicinity of the atmospheric pressure. And also P at B, pressure at B, is also equals to the atmospheric pressure, because it's in the vicinity of the atmosphere. So if we measure based on the gauge pressure, we can assume that PA equals to PB equals to P atmosphere equals to 0. Also, we know that the velocity at B is much greater than velocity at A, at point A, which is the tank or reservoir, because it has a large cross section, so it moves very, very slowly down, right? So the velocity here is much smaller than the velocity here, right? So we can assume that VA is so this has a downward motion. VA is almost 0, so we can make this assumption. So now that we have these assumptions, we can write the energy equation between point A and B. So we can start with ZA plus VA square over 2G plus PA, which is 0, so I don't write it down, equals to Z at B, elevation at B, plus VB square over 2G plus P at B, which is again 0, plus the total head loss. Okay, so I don't know what is the total head loss, and also I know from this assumption that VA should be 0, right? So I just write it down as 0, and the only unknowns in the problem are HL. I don't know what is HL, and also I don't know what is VB, right? So these two things I have to find based on the information that is given in the problem. So let's first write what is HL, what is the total head loss in the system. So the total head loss is equals to the sum of minor head losses in the system plus major head loss in the system. The major head loss is caused by the pipe friction, and we have 3 pipes here. So as you remember, in a pipe system, a series pipe system, we can write that the total head loss from a point A to B is the sum of all the head losses in each pipe. And that is what I am doing here. I just sum all the head losses in the system because I have a series pipe system. Okay. So the first one is the entrance loss. So the loss that is here, that is caused here. We have a loss here because the flow is coming here from, and we have a sudden contraction in the fluid. So that is the first one. The second one is the major head loss in the system, which is due to the pipe friction, and it occurs in all these 3 pipes. Okay. And the third one is the head loss due to this elbow, which is a minor head loss. And the fourth one is the head loss due to this valve, this half open valve here. Okay. So let's see what are these. So the first one is KL, is a minor head loss, so I can write it as KL times VB square over 2G. So here I have made one assumption. You might say, why VA, not VA? It's not, the V here is not VA, right? Because VA is here. And if you write the, mass conservation equation, which we had here for 3 pipes, we had Q1 equals to Q2 equals to Q3, right? So I can write it down here. I can write Q at here equals to Q here, Q at pipe 1, Q at pipe 2, Q at pipe 3. They all equal to each other, and because the diameter of the pipes are all similar in these 3 pipes, therefore I can say that V at 1 equals to V at 2 equals to V at 3, which equals to VB. So here I just can write VB square instead of V at pipe 1, which should be here. So that is why we have VB square over 2G, and 1 is the KL, the loss coefficient for an entrance. So if you have an entrance, you can go to the tables in the book, and you will see that for this type of problem where we have a contraction, the head loss and the loss coefficient should be 1. So this is the head loss due to the entrance is 1 times VB square over 2G. The second one is going to be F times L, the length of the pipe, over D times VB square over 2G. And again, because VB is the same here across all the pipes, the velocity is the same. I can just write VB, and I can and D is also the same, and I just need to calculate the total length of the pipes to find the major pressure or major friction head loss in the system. And the third one is the head loss due to the elbow, and as you can see, I can write it down as KL elbow, which is the loss coefficient of elbow multiplied by VB square over 2G. And the last one is the loss coefficient of the valve times VB square over 2G, and this one is given in the problem. KLV equals to 5, so I just write it down as 5. So if you go to table 8.2, you will find you can find the loss coefficient for this long radius elbow, which is threaded, and it's 0.7. So I can just substitute it here. So I will just substitute it here, and then I can find the total head loss in the system. So the total head loss is gonna be, I have VB square, I can just factor it, VB square over 2G. It's gonna be 1 plus 0.6 is going to be 1.7 plus 5 is going to be 6.7, which I wrote it here, plus F multiplied by the total length of the pipes, which is 9 plus 90, right? So I have this vertical pipe plus these two horizontal pipes in which their length is 90 meter. So it's going to be 9 plus 90 over the diameter of these pipes, which is 4 inch. So 4 inch equals to 10 centimeter or 0.1 meter. So I just substitute all the values that we have from the problem, and these all multiplied by VB square over 2G. I just factored it out and wrote it here. So if you calculate this value, is gonna be 967.7 multiplied by F. I don't know the friction factor or F. I have to calculate the Reynolds number and relative roughness to find the friction factor in this pipe system. Okay, so this is going to be the relation for HL, and now I can substitute this into our original energy equation. Okay, so I can simplify the energy equation. I can bring ZB to the left hand side. So I will get ZA minus ZB equals to VB square over 2G plus HL. And I found HL here, if you remember. And I just substituted it into this equation. So I'm going to get 6.7 plus 967.7 times F multiplied by VB square over 2G. And ZA minus ZB, as you can see, this is A. The elevation of A minus elevation of B is going to be 9 plus 3 is going to be 12 meter. Okay, so now I just combine these two together. Again, I factor VB square over 2G, so it's going to be 6.7 plus 1 is going to be 7.7 plus 967.7 times F. So this relation gives me 12 times 2G over 7.7 plus 967.7 over F equals to VB square. So VB equals just to the square root of this expression here. So I just write G as 9.81 and calculate this, and it's going to be 235.4. So this is going to be one relation which relates VB to F, the friction factor. So this is the only relation that I can get from the energy equation. Okay. But in order to find F, I need to know what is the Reynolds number, right? So let's calculate Reynolds number. So Reynolds number is VB times D over nu, which is the viscosity of water. So it is 8.03 times 10 to the minus 7, which is the viscosity over rho, the density of the water. So I just write it down here. And then I have VB multiplied by D, which is the diameter of this pipe. This is a 4-inch pipe, so it's going to be 0.1023 meter. Okay. So I can simplify this and get to this number, 1.274 times 10 to the 5 multiplied by VB. So as you see, Reynolds number depends on VB. And let's calculate the relative roughness, because we want to see, we want to find the friction factor. And in order to find that, we need relative roughness to go to the Moody diagram. Okay. So again, we know the diameter of the pipe, which is 0.1023 meter over epsilon, which is the roughness of this type of pipe. So this is a steel pipe, commercial steel pipe. So I go to table 8.1 in the book, and I find this roughness value for that, which is 4.5 times 10 to the minus 5, and this is gonna give me this is gonna give me the d over epsilon, which is 2,273, and this is gonna be the relative roughness length, relative roughness, which is 0.0004. So I have Reynolds number, which is a function of VB, and the relative roughness. So as you can see here, in order to find friction factor, we need to know the Reynolds number, and in order to know the Reynolds number, we need to know the velocity at the pipe. So we don't have velocity at the pipe. So what can we do? So in this type of problems, as you can also remember, this is a type 2 problem. We need to do iteration, right? So we need to use iterative methods. So we need to iterate, and we can use either you can iterate over VB, or you can iterate over F. So these are two variables in the system in your equations. So this is one equation that we have, and this is gonna lead to the second equation from the Moody diagram. So you can either iterate through over F or VB. So I'm gonna iterate over F because it's easier. So I assume that F is 0.02. So this initial guess comes from some experience, and also you can look at this relative roughness in the Moody diagram, and just follow it and see where is a possible range for F. Okay, so you will get a possible range of F, and then you get an average of that. So this is like the first initial guess for me. So that is my first guess. So I assume F is 0.02. I calculate VB from equation 1. So it's going to be 235.4 over 7.7 plus 967.7 multiplied by 0.02 equals to 2.95 meter per second. So this is gonna give me this value, and now that I have VB, I plug it into equation 2. I find the Reynolds number. The Reynolds number is gonna be 3.76 times 10 to the 5. With relative roughness of 0.0004, I go to the Moody diagram, and I find that the F should be 0.018. So my first initial guess was not that bad, but it's not correct. So in order to get a more accurate F, I need to set the second guess as F equals to 0.018. Okay, so I start everything again by assuming that F is 0.018, and I substitute this into equation 1, and then I get VB equals to 3.06, and Reynolds number is gonna be 3.89 times 10 to the 5. I go to the Moody diagram, and I see again that F is almost equal to 0.018. So this tells me that I have converged, because my guess, which was 0.018, equals to the final value I found from Moody diagram. So I converged to a constant value of F, so I can say this is the correct answer for this problem that satisfies both equation 1 and equation 2. So F is 0.018, and VB is gonna be 3.06 meter per second for this problem. So now I can solve Q here, the flow rate at VB, which is what the problem wants from me, is gonna be AB times VB, and AB is the cross section, the area here is pi multiplied by d square, which is 0.1023 squared over 4, PD squared over 4, multiplied by the velocity, which is 3.06 meter per second. It's gonna give me the final answer for this problem, which is the flow rate at B is 0.025 meter cube per second. So this is the final solution for this problem. Okay.